Last video we look at the slenderness ratio compared with the limit, and we found that column is slender. Now in this video we're going to look at clause 10.4.2 to find the moment magnifier for the brace columns. As we notify at the start of the examples is a brace column, so we are designing it for brace columns. So the moment magnifier is delta B is equal to Km over 1 minus n star over nc. N star is the design load that we take it 3618 kilonewtons. Now in these equations we need to calculate Km and factor Km and the buckling load nc. So let's talk about the Km factors. The Km factors is 0.6 take away 0.4 m1 star over m2 star, and this m1 star over m2 star is the ratio of smaller to the largest. And we look at that conditions here, therefore we took it -1. I think in the last videos we saw that m1 star over m2 star is -1 based on these conditions. So for that conditions we substituting that is -1 here. So 0.6 minus 0.4 times by -1 gives me 0.6 plus 0.4, it gives me 1. So that is the Km. So we found Km, we know n star design axial load, and we going to calculate this buckling load from the clause 10.4.4. Just over the page here we can get this equation for buckling loads. I have written this equation here. I am not reading it, that one, but let's find out the parameters that we require to calculate the buckling load. So first beta D is equal to G over G plus Q. I think if you come here, there is a beta D, that's G over G plus over Q. Now G is our dead loads, that is 1832 kilonewtons. Given in the examples, live load is 885 and 1832. So I substitute that value, gives me the beta D equal to 0.67. Now once we found that beta D, let's check. There is a condition here that we need to check for the beta D, saying that length over ratio should be, so it should be taken 0 when these two conditions are met. So length over ratio is 40, so that is fine. We have a L over ratio 28, so that's condition met. But second conditions, let's check it out. N star is 3618 given in our examples, that is the design load 3618 kilonewtons. And we can calculate m star over 2d 86. I think in our examples there is a m star given 86 kilonewton meters. So 86 over 2 times by, that is in kilonewton meters, so we can keep this d as a kilonewton in the meters. So the 450 millimeters divided by thousands to get it in the meters. So that is kilonewton meters, that is meters, so it gives me 96 kilonewton. So let's check that 3618 kilonewton is greater than 96 kilonewton. So we don't take beta D equal to 0. We don't take it because this condition has not met. Is n star is greater than m star 2d. In that case, whatever we calculate beta D in just now, that will just going to take that beta D equal to 0.67. Otherwise, if that condition, both conditions will met, we take beta D equal to 0. Now we need to determining that capacity factors times MC. I think in our examples, in our buckling load we need to calculate this value. For G equal to 0.8, I think at the start we calculate this G 360 over 450. Basically this 360 over 450, that's give us 0.8. Now we have various charts that we can use it. I think this chart is taken from one of that book. So this chart is giving us G equal to 0.8, G equal to 0.9. Now we have G equal to 0.8 and concrete compressive strength 25 megapascals. Yes, concrete compressive strength 25 megapascals. So on the y-axis, it has this non-dimensional moments 5 mu over bd square, and on the x on this y-axis you have 5 nu over bd. So let's calculate those. N star over bd 3618 times by 1000 to convert into the newtons. 3618 basically coming from here, 3618 given in our examples, over BD, this is the B 450 and that is D 450. so that substitute here gives me 17.9 megapascals. We can also calculate this m star over bd square. Design bending moment given us 86 kilonewton meters. Substitute here times by 10 to the power 6, because we like to convert these kilonewton into newtons and this meter into millimeters, so we multiply by 10 to the power 6. B is 450, that cross sections B is 450, D is 450, so BD square equal to 0.95 megapascals. 5 mc equal to BD square equal to 3.9. Well, how is 3.9 is coming from? Let's do it this one. So if you take the ruler, and that is 0.95, so that is almost 1, so we can draw the one line here, and there is a 17 here, just line here. So if the 17 here on this line, where is the 1? So 17, and if you just draw a line here, and if you come here, you will get this locus point, locus line, and on that locus line, if you just draw the line here, from here, that will give you 3.9 approximately. That is the value of 5 mc bd square. That value you're going to get it here, 3.9. So I hope you understand. I can repeat here 1, because there is a 1, 0.95 is almost 1, so there is a 1 here. So you draw the line from here, that is the moment. The load is 17, around 18, so around 18 you draw a line here, intersect here at this particular point, and from that point you can just come across here. There is a lotus line. On that lotus line, if you draw the line here, you will get the moment 3.9 moment that we just get here. So 5 mc equal to 3.9 times by 450 times by that same thing that we done it here. So we can calculate 355, 387, 500 Newton millimeters, divide by 1000, divide by 1000 give us 355 kilonewton meters. So now we have all the parameters to calculate this buckling load. Equation of the buckling load, that written here, enclosed 10.4.4 pi square Le, effective length. I think in our last video we calculate the effective length. Let me show you that effective length calculation. Here you go, effective length we calculated 3783 millimeters times by 182. D0, how are we going to get the D0? D0 is basically 450, take away this 45. So 450 take away 45 is give you 405. Is that from the reinforcement here to the top of this edge is a 405. So that is D0. We just calculate this 5 mc 355 and just times by 10 to the power 6 into the Newton and millimeter. So that's multiply 1 plus 0.67 beta D we calculate as 0.67, and that gives me this in the newtons. Let me write this one in the newtons, and then you divide by 1000 to get it in the kilonewtons. So I think that's the buckling load, and in the next videos we're going to look at these moment magnifiers, and then we finish that examples in the next video. Thank you.